Hey there everybody. In the previous video I gave a global overview of SIR models and a tiny bit of their history without actually giving you the differential equations. So in this video I want to give you the differential equations and then we'll talk about solving them and how you interpret the solutions next time. So in class on Friday. So what are we going to do in these slides? It looks like we're going to do a lot, but I'm going to move through this as quickly as I can. And really goals 3 through 5 and 6, I guess, are just saying I'm going to build for you a system of DEs, and I need a bit of vocabulary to do that. But once I have some vocabulary, I'll build a system of DEs for you. We will look at it and be like, ah, yes, there's a system of DEs, and then on Friday we'll solve them. First, though, let's just review what math modeling is, just to reset where we are, because that's what we're doing for the last week or so of class. So what is math modeling? This is not news to you, but it's building a mathematical tool, usually an equation or system of equations that allows you to make predictions in a system you're interested in. So modeling has 4 steps. You have to state your assumptions, and then those assumptions drive what model you write down. So if you're going to neglect air resistance, you'll write down a different equation than if you take air resistance into account, things like that. You solve your model. So this is a purely mathematical step right here. You then interpret the results. So you ask yourself, does this make sense what this mass on a spring is doing? Whatever. What is my model predicting about these two populations over time? And then, if possible, you check your model against actual data. So you try to evaluate how good your model is. Now, we have done none of this in this class so far. We're going to do a little bit of it with SIR models. Not much, but this actually is an important step of modeling in the real world, so we'll talk about it a little bit. So for the SIR models, I need to do this. I need to state my assumptions and then set up a system of DEs that mirrors those assumptions. We're not going to solve anything or interpret anything for now. We're going to save steps 2 through 4 for class later. So first, what variables do I care about during an outbreak of something like the flu or whooping cough or measles or whatever? Here are the variables I care about. The number of people right now who are infected, although infected is the term people use, but really what they mean is infectious. So just because I have a virus in my bloodstream and therefore I'm infected, doesn't mean I can infect other people. But anyway, when you hear infected in these models, you should always think infectious, capable of infecting other people. The number of people who can no longer be infected, those people who have recovered from the disease, also those people who have died. This model counts those people as recovered, mainly because they're not infectious anymore. Also, later we'll incorporate vaccinated people into this group. And then, of course, the people who are still susceptible. Those are the 3 variables we care about. All 3 of those variables are functions of time. All 3 of them, their value depends on what day it is today. So there's a 4th variable t, which is the independent variable in all of this. We are going to measure it in days. You could also do things like measure it in weeks or measure it in hours, I guess, if you wanted to. But days is pretty standard. Okay, so we're going to use 2 related sets of dependent variables. These are the 3 I just said. The number of susceptibles, the number of infecteds, the number of recovers. Now notice, SIR. Everybody see that? SIR model, right? It's all coming together here. We're weaving a tapestry here. So SIR model is because of susceptible, infected, recovered. Now, in practice, a lot of times, if you're going to draw solution graphs, if you're dealing with a huge population, this curve might start up at 10 million people. The scale can be sort of hard to deal with. So sometimes you deal with just proportions or fractions. So S of t, in here, I guess I should say, is the total population. So lowercase s is the proportion of people susceptible, lowercase I, proportion of people infected, and so on. So when you build an SIR model, you either have capital SIR or lowercase SIR, depending on if you want to deal with raw numbers or you want to deal with fractions. The graphs will tell you the same thing. It's just the scale's a little nicer on these because now the vertical axis only goes from 0 to 1, right, when you're only dealing with fractions. So here are some questions that we would think about in class. So if you like, you can pause the video now and think about these, but you can think about, well, over time, the proportion of susceptible people, what happens to them if you have a disease outbreak? Over time, the proportion of recovered people, what happens to them? What about the proportion of infected people? What happens to them? And you could sketch a graph. So you can see what you think about that if you want to. We're going to see these graphs on Friday, so I guess you don't have to think about it. Okay, so what are the model assumptions? So what assumptions drive the differential equations I write down? Assumption 1, the total population is constant. What does that mean? It means I'm neglecting births. I am neglecting immigration. So you might say, you can't do that because in real life people are born and people immigrate. And I say a model is just an approximation. And so especially if we're dealing with short time frames, like a year or less, you know, do you really need to worry about babies being born during that year or those maybe even just 2 months? I don't know. It depends on your outbreak. But over a short time span, you can ignore immigration and births without losing too much information. So related to that is nobody is added to the susceptible group. So how would you add people to the susceptible group? Well, you could have babies be born. You could have immigrants come in. Also, I guess with some diseases, after a while, your immunity wears off if you've had the disease. So it's possible maybe that you could be added to the susceptible group because your immunity wore off. But we're not going to deal with any of that. So here's the flow we're dealing with. Susceptibles become infecteds if they go anywhere, and then infected people recover. Where again, recover could mean you died. So we don't have like a separate group for dead people. Yeah, assumption 3, the only way an individual leaves the susceptibles is by becoming infected. Oops. Assumption 4, an infected person stays in the infected group on average for K days. So on average here is important because as I'm sure all of you know, if I get the flu and you get the flu, we might not have the flu for the same length. You know, I might be sick for 3 days, you might be sick for 5 days, who knows, right? So on average though, a fixed fraction of the infected group recovers during any given day. So if on average the flu lasts for 3 days, then on a given day you'd expect a third of that group to recover, is what this is saying. Oh, yeah, so if K is 4, right, on a given day, a fourth of the infected people should recover. And again, a reminder, when I say infected, I really mean infectious. Okay, we also assume that the number of susceptibles depends on the number of people already susceptible. So in other words, capital S depends on itself. The number of individuals that are infected and the amount of contact between them. So as I'm sure you know, this population here, like what would cause it to go down? What would cause this population to decrease is interaction between people who can get sick and people who are sick. The more interaction you have between those two groups, the more susceptibles will leave the susceptible group. So let's let tau be the probability that a susceptible person becomes infected given a contact between the susceptible person and this infected person. And tau is sometimes called transmissibility. So suppose each infected individual has an average of C contacts per day with other people in the population. Then I claim this: the average number of contacts that an infected will have with susceptibles on a given day is given by this number here. So you take the number of contacts times the proportion of the population that is susceptible. So you could ask, on a given day, how many new infected individuals will a single sick person generate? And the answer, you have to think about it for a minute, but again, I'm trying to do this as quickly as possible. I know my voice is not particularly appealing to listen to for long stretches of time, especially in this video format. So anyway, let's take an example here. Suppose tau equals a third. So what does that mean? That means when a susceptible and an infected bump into each other, there's a third of a chance that the susceptible person becomes sick. So all we're saying here is that, you know, if I have the flu and you don't, if I like cough in the same room as you, you're not, or I cough next to you, I don't know. There's no guarantee you get the flu, but there's some probability you'll get it. So tau is just measuring that. And again, tau is probably an average or something. Okay, let's say that each infected individual has now 6 contacts per day. So this particular average infected person is not sitting in their bed at home, right? 6 contacts per day, they probably should be at home, right? But anyway, and suppose today, half of the population is susceptible. What would that mean? On that day, a given infected person has 6 contacts with other people. Half of the population is susceptible. So we would expect, on average, 3 of those 6 contacts to be with susceptible people. Okay, so you have 3 interactions with susceptibles. Your probability of transmission is a third. So of those 3, you'd infect 1 of them. So given these 3 choices here of transmissibility, number of contacts per day, and proportion of people who are susceptible, given those choices, you would expect each infected person to give you 1 new infected person every day. So that's what tau, C, and S are telling you. Now in the model, we're going to sort of just multiply tau by C to get this number called B, which is called the effectiveness rate. So what I'm saying is each individual infected person would generate B times S of T new infecteds per day. So C times tau times S, right? Tau times C times S, what was that? 1 new person. So here I'm just doing tau times C times S to get this. So again, you basically just roll tau and C into this B, and this B is what we'll plug into our model. So a quick note about that B, this effective contact rate. One way of thinking about it is the number of contacts by an infected person per day sufficient to spread the disease, but not guaranteed to spread the disease. So again, if I cough and I don't cover my mouth and you're 3 feet away from me, there's some probability you'll get my disease, but it's not guaranteed. So here's one way the homework can talk about that kind of thing. So if I say each infected person has 1 contact sufficient to spread the disease every 2 days, you would take this 1 divided by 2, and there's your effective contact rate. Okay, so now let's start building the model. So here's the susceptible equation. So let's think about this. What I'm saying is, if you want to measure how the susceptible population changes per day, I'm claiming on a given day, this many people leave the susceptible group, and leave because there's a negative. So the population of S is going down. So I claim this many people leave the susceptible group on a given day. So again, in class, I would ask you to do all this, but let me just point out, way back here, we said, and when I say we, I mean me, I guess. Where did I say it? Each infected person will give you this many new infecteds on a given day. Each infected person. So what if there are 30 infected people? You would take this and multiply by 30 to get the total number of new infecteds. What if there were 50 infected people? You'd take this, multiply by 50 to get the total number of new infecteds on a given day. So that's what's happening here. Each infected person will give you this, so then you got to multiply by all the infected people out there to give you the total number of people leaving the S population on a given day. And again, the negative sign here because you're leaving. So negative because S is decreasing over time as they interact with the infecteds. I is there because of what I just said. And now if you take both sides of the equation and divide by capital N, the total population, this capital S becomes a lowercase s, and this capital I becomes a lowercase I. You're dividing by capital N. Yeah, notice this, right? This is all the way back in chapter 2. Rate in minus rate out. So this is the rate out. This is how many people are leaving on a given day. The rate in is 0 because nobody's being added to the susceptible group. Again, there's no births, no immigration, nothing like that in this model. Okay, so let's think about the recovered equation. If you wanted to think about the rate of change of the recovered population, let's think about that. So I'm claiming that the proportion of recovered people per day changes like this. You take the infecteds and divide by K. Why would that be true? Well, again, if we were in class, I'd make you think about it, but we're not in class. So each day, recall, I just said, like 10 minutes ago, if the infection lasts 4 days on average, then you'd expect 1/4 of the people to recover a day. If the infection lasted 3 days, then 1/3 of the people will recover a day on average. So this is how many people are recovering on a given day, and where do these people go in terms of our model? They go to the recovered population. So here's an equation for the rate of change of recovereds. Again, it's just saying, if you want to know how many people are added to the recovered group per day, just take the number of infected people and divide by the length of the infection. That gives you an average amount of people leaving the I population and flowing into the R population. And then if you divide capital R by capital N, capital I by capital N, you get this. So here are two separate recovered equations. So here's the proportional one, and here's the raw numbers one. So we have differential equations to deal with susceptibles. We have differential equations to deal with recovereds. To build a complete model, we now have to build differential equations to deal with infecteds. And again, if we were in class, I would make you do this. But just note, this equation here is true because I said a long time ago the total population is fixed at n. Therefore, if I differentiate everything in sight, this becomes an S prime, I prime, R prime, 0. This is a constant. Okay, so this is true here because the total population is constant. So you can start to see why that assumption might help you set up an equation for capital I or lowercase I. Because now, if we know S prime, we know R prime, then we know I prime for free. Because we just put the other stuff on the other side. And that's what happened here. So again, having a constant population might not be literally correct. It's not. But surely over short time spans, it's fine. And also it lets you do this little bit of math right here. Okay, so here is the inflow into I, and there is the outflow. So rate in minus rate out. Classic chapter 2. So now you have three differential equations for the fractional variables. S prime is this, I prime is this, R prime is this. B and K are parameters that depend on the particular disease and the behavior of the population. So K here, that was the length of the disease in an average infected person. So that's sort of a function of the disease. You know, so for the flu, K is much smaller than for COVID-19, for example. The flu, it hits you for like 2 days and then it's gone on average. COVID-19 on average hits you for much longer than 2 days. And B here, this effective contact rate, that's like a measure of contagiousness. So that depends on how people behave. As we all know, right, COVID-19 could be far more contagious than it is if nobody wears masks and if nobody washes hands and things like this. Okay. Now, oh yeah, and also in order to solve the model, you can't just have differential equations. You need some initial conditions. So there's just some initial amount of susceptible people. There's some initial amount of infected people, and we're always thinking about starting small. So at the beginning of an outbreak, there's almost nobody infected, but notice this is not equal 0. Somebody's infected, just not very many. And then down here, initially, the proportion of people that are susceptible is almost everybody. The proportion of people who are sick is almost nobody. And then initially, if you don't have a vaccine or something, the number of recovered people is literally 0 at the beginning of the outbreak. Okay, so here's the complete SIR model with proportional variables. So 3 differential equations, 3 initial conditions. And here's the complete SIR model with just the raw numbers. So you can see already this looks nicer to me than this. So some people like the proportional model for that reason also. But anyway, you can use either one. It's fine. Just depends on if you want to deal with fractions or not with fractions. It's up to you. So I want to do 2 more quick things here. I want to talk about these parameters of the model and talk about what we can control. And then I want to show you a Washington Post article that's a little out of date now, but it has a nice way of thinking about these interactions between the populations. Okay, so there are 5 parameters in the model. Which of these can we hope to control? Some of them we probably can't control at all. So the length of an infection, until you create therapeutic drugs that can maybe shorten that length, you probably can't do much about that. The initial amount of infecteds, again, unless you're going to like quarantine everybody all the time, you probably can't keep that super low or at 0. Right? You'd like this to be 0 all the time. Nobody's infected, but you can't really control some small outbreak somewhere. Now, the initial proportion of recovered people, if a vaccine exists and people use it, you can make that pretty high. So a vaccine is a shortcut to being recovered. So thereby you could then make the initial proportion of susceptible people low and maybe stop outbreaks that way. This measure of contagiousness here, B, as we just said, right, you can make B small by washing hands, social distancing, quarantining. That's the most extreme thing, right? So society has some control over this. Not so much over this until you make therapeutic drugs. Okay, let me make 2 more quick comments real quick. This kind of thing here, see capital S times capital S, capital I, these are very Lotka-Volterra type terms and competing species types terms also, but in particular Lotka-Volterra. So what is this saying? It's saying that as S and I interact, that tends to diminish the S population, but then increase the I population. So there's some sort of nice parallels here between what we're doing now and predator-prey in that sense. You have different populations interacting to the detriment of this population, but to the benefit of this population. So that's a nice thing to note. Now finally, on Moodle, I'm going to post this link. This is outdated now, but it still has some nice visuals. So they're still talking about flattening the curve because this is March 14th, 2020. But I want to show you the visuals real quick, just so you can see the kind of thing we're doing. Okay, so check this out. They're going to have a simulation where you have 199 healthy people, one sick person, and nobody has recovered yet. And we're going to imagine these populations interacting. So here we go. Sick person is doing this, and then boom, they make another sick person, right? See, every time an orange hits a blue, they turn orange. And then over time, see, recovered one. So pink is recovered. So over time, people recover. So now the screen is entirely orange and pink. And now the pinks are taking over as people recover. Now, one thing to note about this model that the Washington Post has, there are, of course, many issues with it you could point out. It's just a little tool, a little visualization tool. But one thing to notice is when sick people bang into non-sick people, this model assumes a guarantee the new person becomes sick. So this simulation doesn't have our tau built in there as a third or something. The probability of creating a new sick person is 1, according to this model. So that's one thing to point out. Also, generally speaking, once you're sick, I see people just moving at random here. That's not usually how people act. That's sort of cute, though. And then here, see, this has like a quarantine. So imagine this is like, yeah, in Wuhan or something, right? So if you loosen your quarantine some, see how you open up some space for people to come in and people to get out. So if you loosen quarantine, see, it takes longer for everybody to get sick. See how this curve is rising more slowly? But still, if you let people escape, the sickness just spreads. So that's sort of cute. And then here, here is a model. See, there's not nearly as much movement because a lot of people are, they call it social distancing here, right? A lot of people in this model aren't really moving around. However, a sick person still hunts them down sometimes, right? That sick person is moving all over the place. So in practice, you know, if you're actually just sitting here, not moving, that'd be like just sitting in your house. So in practice, you put like a little quarantine barrier around you, I guess. Also, you could think of these people sitting still as like, as what? Social distancing means they're trying hard not to come into contact, but they might still come into contact with an orange dot at work or whatever, at the grocery store or something. Anyway, but notice, see this orange curve, it builds very slowly now with social distancing. So flattening the curve was a term we used a year ago. That's what you're seeing here, right? The curve is getting flattened. People are still getting sick, but not nearly at the rate they used to be. And I think they have one more. Yeah, so here's more social distancing. So now there are fewer people moving around. See this orange curve, this number is not rising very quickly. So this curve is not rising very quickly. So anyway, here's a cute little thing that you should have in your head when you think about what these models are doing. You're just watching these little dots representing people move around. When sick people bump into non-sick people and the susceptibles, they can turn them into orange dots. And then once you're a recovered person, you can do whatever you want in these models because you're immune. Okay, so next time what we're going to do is we're going to actually plug in some parameters for these models and solve them. So we haven't solved anything yet. So at the end of this video, you should be comfortable with what the models are. 3 differential equations, 3 initial conditions, and be comfortable with where they came from. And then on Friday, we'll actually talk about using them some. So if any of this doesn't make sense, you should, of course, email me or ask on Friday. So I'll see you guys on Friday in the Zoom classroom.